Welcome to the session. In previous session, we have studied the basics of refraction of light ray. So when a light ray moves from a rarer medium to denser medium, the speed of the light ray changes. Due to this, the refracted ray will move towards the normal and there is a deviation in its original direction denoted by delta. So the angle of incidence is equal to angle of refraction plus delta. So when the light ray moves into denser medium, its speed reduces and refracted ray tends to move towards the normal. Whereas when the light ray is incident in denser medium and is hitting the boundary of surface and is moving through rarer medium, the refracted ray, the velocity of light increases when it enters the rarer medium. Due to this, the refracted ray tends to move away from the normal and the speed of the velocity of the light increases. Angle of incidence I is given as angle of refraction minus deviation, that is delta. We have seen this in the earlier session. Now we have also seen when the light ray doesn't and hit the boundary surface obliquely. So when it hits perpendicularly, that is angle of incidence is 0. In that case, there is no deviation in the refracted ray, nor there is any change in path of the refracted ray. So the incident ray, refracted ray will move along the same line, whereas incident angle is 0. So this is called undeviated refraction along same path. Okay, this we have seen in previous session. Now, the first topic today is what are the two conditions which one among them need to be satisfied. So there are two conditions in which undeviated refraction along the same path happens. Let us see one. If you see the screen, consider the first white box. Here the incident ray is traveling like this, hitting the boundary surface at point A, and the refracted ray is moving along the same line. So if you see, there is no deviation, so delta is 0. So I is equal to R here. Angle of incidence is equal to angle of refraction. So the speed of the velocity of the light is not changing. Angle of incidence is equal to angle of refraction and deviation is 0. So this is undeviated refraction along the same path. Now the light ray is moving from medium 1 to medium 2. So let refractive index of medium 1 be mu1 and refractive index of medium 2 be mu2. So for this phenomenon to happen, the refractive index of medium 1 should be equal to refractive index of medium 2. That is, mu1 should be equal to mu2. Then only this undeviated refraction along the same path happens. So this could be one condition that would result in such a phenomenon. Now, if the refractive indices of the medium 1 and 2 are not same, still undeviated refraction along same path can happen. That is the condition 2. Suppose the refractive indices are different, still, now consider this. An incident ray is hitting the boundary surface perpendicularly. That means angle of incidence is 0 here. In this case, the refracted ray moves along the same path and in the same direction. So here there is no deviation, so delta is 0. Then I is 0, therefore R is also 0. So here the refraction is undeviated. So the refracted ray moves in the same path, in the same direction. So the only thing that is changing here is velocity of light in air would be high, whereas velocity of light reduces as it enters glass. Again, velocity of light increases as it enters air. So this is again undeviated refraction along same path. Now here, what is the condition that is leading to this phenomenon? The angle of incidence is 0, that is, the incident ray should hit the boundary surface perpendicularly along the normal. So this is the normal to the boundary surface. So incident ray should hit the boundary surface along the normal perpendicular to boundary, that is, angle of incidence is 0. In this condition, undeviated refraction along same path happens. So these are the two conditions in which undeviated refraction along same path occurs. Okay, so let's move further. In the previous session, we have also seen the basic properties of light: wavelength, frequency, velocity. We saw that frequency for a given source of light, frequency is constant. It doesn't change. Even though light moves through 10 different optical medium, the frequency remains same. It doesn't change. Now wavelength and velocity are the two parameters that keep changing as the light travels from different medium. Now wavelength and velocity are directly proportional. Like if the wavelength is high, the velocity of light will be high. The reason being, I'll draw an analogy. For example, there is a taller man, so his single step will cover more distance. So the single step of a man, walking man, is analogous to wavelength, and the distance walked is analogous to velocity, or distance walked per second is analogous to velocity. So if the man is taking longer step, he will travel more distance. So this analogy, if you remember, it applies to wavelength and velocity of light. So if the wavelength is less, velocity of light will be less. If the wavelength is more, velocity of light will be more. Okay. Now since the frequency of any light is constant, if we rearrange this, like lambda is equal to V by F. Now here frequency is constant, so look at the value of this expression V by F. Because denominator is constant, if I increase velocity, what will happen to lambda? So this V by F expression, what will happen to it? It will increase. So if I reduce the velocity, what will happen to lambda? It will decrease. Okay, so wavelength is directly proportional to velocity. So if the velocity increases, wavelength increases. Okay. Now consider a light ray that is moving through uh, optical medium 1 and another optical medium 2. Let lambda 1 be the optical wavelength of optical medium 1, lambda 2 be the wavelength of optical medium 2. Let v1 be the velocity of light in optical medium 1 and v2 be the velocity in the optical medium 2. Now, since f is constant in this expression, since f is constant, if I take the lambda other side, f, I can write it as v by lambda, right? So f is constant. So the same thing is here. So when f is constant, v by lambda is constant. So if wavelength in medium 1 is lambda 1 and velocity in medium 1 is v1, then v1 by lambda 1 is constant, which is fixed for a source of light. That means if there are two optical media through which the light is passing, then velocity of light in second medium, its ratio to wavelength of light in second medium is also constant, and they are equal. So V1 by lambda 1 is equal to V2 by lambda 2. Likewise, we can continue Vn by lambda n. Okay. So if I rearrange this as lambda 1 by lambda 2, so lambda wavelength of light in first medium to wavelength of light in second medium is equal to velocity in first medium by velocity in second medium. So this relationship between wavelengths and velocity of light is evident. So lambda 1 by lambda 2 is equal to V1 by V2. It makes sense. See, it makes sense. They are directly proportional. So if it is 1 by 2 here, it also should be 1 by 2 here. Okay. Now suppose if the first medium is replaced with air, then the velocity of light in air is denoted by c, that is 3 into 10 to the power of 8 meters per second. So this is another way of expressing the same expression. So remember this, lambda 1 by lambda 2 is equal to v1 by v2. This is the relationship between wavelengths and velocities of light in two media. Let's move further. Now, refractive index, we have a fair idea. Let us define refractive index. We saw Snell's law. So first Snell's law, what it says, incident ray, normal and refracted ray at the point of incidence all lie in one plane. Second Snell's law, the ratio of sine of angle of incidence to sine of angle of refraction for a given pair of media is constant. So this is Snell's second law. So the refractive index definition is derived from Snell's second law and is denoted by mu 1 to 2. When I write it as mu 1 2, that means this is refractive index of second medium with respect to first medium. Okay, then how is it defined? In terms of sine function. Sine ratio of sine of angle of incidence in first medium to ratio of to sine of angle of refraction in second medium. This is how it is defined. And mathematical expression, how is it written? Sine I by sine R, where I is the angle of incidence in first medium and R is the angle of incidence in second medium. So this is one way of defining refractive index. So here the refractive index in second medium is defined with respect to first medium, which can change. Okay, so when such, it is a relative sense of the refractive index that we are defining. So when you are defining relative sense, then it is always the sine function in terms of which we are talking. Okay, now to measure the refractive indices of different optical media, what scientists have done is they have taken the speed of light, which is constant in vacuum or air. They have taken this medium, vacuum or air, as a standard, and the refractive index of vacuum or air is taken as standard, and other optical media are measured with respect to this standard. So because the speed of light or velocity of light in vacuum and air is constant, and because the refractive indices of various optical media are being measured with respect to air or vacuum as medium, standard media, so velocity of light c makes its way into the definition of refractive index. Let us see how. So the same expression mu 1 to 2, if I am replacing 1 with air, okay, then I can write it as mu 2 air. Then this refractive index is called absolute refractive index. So earlier it was relative sense, now it is absolute refractive index. So when I am mentioning the second medium, I can even drop the subscript 2. Okay. So when you are taking vacuum or air as a threshold or a benchmark and measuring refractive index of a medium with respect to refractive index of a vacuum or air, you can simply write it as mu. And when I say mu of glass, that means absolute refractive index of glass when the first medium is vacuum or air. Okay, so this is the absolute refractive index. Now, how do we define this absolute refractive index? Because c, that is the velocity of light, has made its way into the definition. So it is defined as ratio of velocity of light in vacuum or air to velocity of light in the medium. So mathematically, absolute refractive index is defined as a ratio of velocity of light in vacuum or air to velocity of light in the medium. Okay. So there are two ways in which the refractive index can be expressed and measured. One is the relative sense of refractive index, where it is defined in terms of Snell's second law, the ratio of sine of angle of incidence to sine of angle of refraction. So that is refractive index of second medium with respect to first medium. The second way of defining refractive index is absolute sense, where the first medium is considered as vacuum or air. So in the absolute refractive index in absolute sense is defined as ratio of velocity of light in vacuum or air to velocity of light in the medium. So these two are these two ways of defining refractive index. I hope it is clear. Okay. So let us move further. Now consider these three equations. See these three expressions, they flow from refractive index of the they flow from definition of refractive index. See here. So it is the same thing that I am expressing here. So refractive index of 2 with respect to 1, it can be written as velocity of light in medium 1 to velocity of light in medium 2. Likewise, absolute refractive index of 1, I can write it as ratio of velocity of light in air or vacuum to velocity of light in medium 1. Likewise, absolute refractive index 2 can be measured as ratio of velocity of light in vacuum or air to velocity of light in medium 2. So these three expressions are derived from this definition of refractive index. Okay. So now we'll move further. So let us call the first expression as equation 1. Okay. Now rearranging this expression, if I take V1 this side, then V1 becomes C by mu1. Okay. Likewise, if I take V2 here, V2 becomes C by mu2. So this V1 is equal to C by mu1 and V2 is equal to C by mu2. If I substitute these two values in this expression, okay, so mu mu to 1, that is refractive index of second medium with respect to 1, can be rewritten as C by, so we are writing C by mu1 and V2 we are writing C by mu2. So if I simplify this, C by mu1 into mu2 by C, so CC gets cancelled, so mu21 will be equal to mu2 by mu1. So this is the relationship between absolute refractive index and relative refractive indices. So what does that mean? So if I have a refractive index of medium 2 with respect to medium 1, if I have refractive index of medium, absolute refractive index of medium 2, and if I have absolute refractive index of medium 1, then what is the relationship between them? So the relative refractive index of medium 2 with respect to 1 is equal to absolute refractive index of 2 by absolute refractive index of 1. So this is the relationship between absolute and relative and absolute refractive indices. Okay. So now if I take this mu1, this value, and substitute it here, then what I will get, instead of mu21, I am writing mu2 by mu1, then right side v1 by v2. So this is the relationship between refractive indices and velocity of light in the media. So mu2 by mu1 is equal to v1 by v2. Okay. Now if you see this, v1 by v2 is also equal to lambda 1 by lambda 2. We have seen that earlier. So if I substitute, if I use that equation here and equate it to here, so this is also equal to lambda 1 by lambda 2. So that gives us the next relationship. Mu2 by mu1 is equal to lambda 1 by lambda 2. So these three relationships, one is the relationship between absolute and relative indices, refractive indices, the relationship between refractive indices and velocities, then the relationship between wavelength and velocities. Now I will give a memory pack how to remember it. See, wavelength, it is always, it follows, because wavelength and velocity are directly proportional. So if you are following 1 and 2 like this, v1 will also be 1 and 2 because they are directly proportional. We saw that man walking analogy. So if the single step is longer, then distances will be longer. So directly proportional. So wavelength lambda 1 by lambda 2 is v1 by v2. But when you take as mu, that is refractive index, mu1 by mu2, this pattern will reverse v1 by v2. Okay, now how to remember this? See, once you see refractive index mu, that means light. Refractive index means light. Light means inverse. See, reflection is always in, image is always inverse. You remember that? So once you see a refractive index, then it will be inverse. So if it is 1 is here, then 1 will come here. If 2 is here, 2 is here. That will help. This analogy will help you remember this relationship. Okay. Then you also know like mu21 mu21 is equal to mu2 by mu1 mu2 by mu1. So this is one more thing. And can you think of relationship between this and this? Using these two, you can also derive a relationship between lambda and refractive index. So using these two, can I write it as, I don't have space here, so I'll write it here. So lambda 1 by lambda 2 is equal to, see, lambda 1 by lambda 2 is equal to mu2 by mu1. So this is also one. So all these relationships you can easily remember. See, the only memory pack that I can give you is, when you see lambda and velocity, they are directly proportional quantities. So same pattern. If numerator is 1, it will be the 1 and 2 in the same pattern on both sides of the equation. But when you are seeing refractive index, that means inverse image will be inverse. So inverse creeps in. So the relationship, so if numerator is 1, on the right side numerator will be 2. So it will be inverse. So if you remember this analogy, you can remember these relationships forever. Okay, let's move further. So these relationships, you should make a chart of them and keep looking at them subconsciously. So in that way, you can recall them in exam. So I suggest you jot down these relationships with bold letters and stick it somewhere where you can see every day. Subconsciously, if you see, then it stays in your mind. Let us move to the next point. What are the factors that affect refractive index in a medium? So we have seen that refractive index like it changes from one medium to another. So within the medium, on what factors does this refractive index depend? Let us see. Let me pull out the last session's PDF that will help you. Okay. So this we used in last session. So if you consider this, we are moving from we are moving from rarest medium to densest medium when you go down. Okay, keep this analogy in view. So what are the factors that affect refractive index of a particular medium? There are three factors that refractive index of any medium depends on. One is the velocity of light through that medium. So if the velocity of light through a medium is high, then the refractive index will be low. See here, vacuum here, the vacuum was the rarest. So refractive index is highest in vacuum, that is 1. So here the refractive index will be highest. Okay, so the velocity of light and refractive index are inversely proportional. If the velocity of light is high, refractive index will be low. So as you move down here, like this is the densest. Okay, so in densest the velocity of light is minimum, so refractive index of densest medium will be high. So that should give you a sense, like refractive index is inversely proportional to velocity of light in that medium. So if the velocity of light increases, refractive index decreases. One. Second, the temperature of the medium. Suppose we have water and it has got a refractive index, particular refractive index. Suppose I heat the water and I increase its temperature. What will happen to refractive index? So when you heat the water, what will happen to molecules? The gap between molecules tend to increase due to kinetic and absorption of kinetic energy. So remember the platform analogy we used earlier. So suppose there is less congestion because molecules are farther. What will happen to velocity of light? It will move faster. So when you increase the temperature of any medium, the velocity of the light increases. So when the velocity of light increases, refractive index decreases. So clear? So when the temperature increases, velocity increases. So refractive index decreases. So what will happen from here? like it is the same, like temperature, whenever you increase temperature of optical medium, so velocity of light increases and its refractive index decreases as we move the entire spectrum of optical medium. So now third one, refractive index also depends on the color of the light that we are considering. Okay, we know the visual spectrum of light that naked eye can see with Gyor. So the light color varies from violet at one end of the spectrum to red at the another end. So this visible light spectrum, violet and red. Do you know why traffic stoplights are painted red? Because red has got maximum wavelength. Red color has maximum wavelength. Therefore, the red light will have maximum velocity. So a person who is at a longer distance can see red light more easily or faster than he can see the violet light. So that is the reason, if you want to draw anyone's attention quickly, you paint it as red. So what you, from this analogy, you should recall that wavelength of red is high, velocity of red is high. The other end of the spectrum, that is violet, if you see here, one end of it is red, so it is maximum wavelength and maximum velocity, and the other end will be minimum wavelength and minimum velocity. So now when you look at the visible light spectrum, it has got different wavelengths and different velocities, but refractive index of vacuum or air doesn't change with color. Let it be any color, refractive index of air or vacuum is same. That is why we consider it as a standard to measure other refractive indices. So in vacuum or air, color has got no effect on refractive index. But all other optical media except these two, except this first one and second one, all other optical media, the color of light has an effect on its refractive index. Now what effect does it have? If you consider violet, it has got minimum wavelength, minimum velocity. So when the velocity is minimum, refractive index will be maximum. So refractive index will be higher for violet light when compared to red light, where refractive index of red light will be minimum or lesser compared to violet light. The wavelength of red light is high, therefore velocity of red light will be higher. So as we move from left to right in the visible light spectrum, so wavelength increases and refractive index decreases. So always, to judge what will happen to refractive index, consider velocity. The velocity is high, refractive index will move the other way. So when you move from left to right, velocity is increasing, wavelength is increasing. So refractive index will decrease. So the three factors on which refractive index of any medium will depend on: first is the velocity of light in that medium. The higher the velocity of light, the greater will be the refractive index. Second, temperature of the medium. If you increase the temperature of the medium, then the velocity of light increases, therefore refractive index decreases. Third, the color of the light. So when when you move from visible spectrum violet to red, the velocity of light increases, therefore refractive index of light decreases. So purple will have maximum refractive index and red will have minimum refractive index. Purple will have minimum wavelength and minimum velocity, whereas red will have maximum wavelength, maximum velocity and minimum refractive index. Okay.